So this is January 2025, Unit 3, paper Pearson et Excel. Question number 1. This question is about qualitative testing for ions. A student was given a solid sample of potassium sulfate. Describe how the student could use flame color to confirm that the solid sample contains potassium ions. Outline the experimental process. So, first of all, what you have to do? First of all, you have to take a nichrome wire. Okay. First of all, you have to take a nichrome wire, or sometime we use platinum wire. The wire should be unreactive. Remember, the wire should be unreactive. Okay. And then what you have to do, you have to take concentrated hydrochloric acid. Okay. You have to take concentrated hydrochloric acid. Hydrochloric acid sometimes is used to clean the wire. Okay. And then you have to transfer the sample to the wire. Let's suppose this is the beaker, and in this beaker I have potassium sulfate, that is K2SO4, and this is the nichrome wire. Okay, then I am going to put this nichrome wire into the sample. So of course, on the wire the sample should be attached. Okay, and then after dipping into this solution, I have to take this wire to the burner, to the burner, just like that. And then I would see the color of the flame. Then I would see the color of the flame. Okay. So finally, I would see the lilac color. I would see the lilac color. Okay. So whenever you are going to test any of the metal ion, especially for the metal cation, so you have to do the same thing. If you remember, I have told you when we were discussing yesterday, Unit 2. So you can see that. You can see that. Uh, okay, okay. Okay, yeah. So yeah, this is the flame test. Okay, so you can see that it's a very simple test to identify cations, especially for group 1 and group 2. What you have to do using dropper, add few drops of concentrated hydrochloric acid to the solid and mix together so that the metal compound dissolves. But in this question, they have already given you the solution, and then to convert and then dip a clean metal wire into a mixture to obtain sample, then hold the end of the wire in the flame and observe the color. These are the colors of different metal cations, so you have to like know these colors, because after knowing the color you would be able to decide what the metal you have in the unknown solution. Like in this, of course, we had potassium sulfate. So that's the reason we got the lilac color, which shows that potassium is present. Okay. Which shows that potassium is present. Okay. So this is of 4 marks. So you have to write down accordingly. Okay. And then they are saying the student dissolved some of the solid sample. The student dissolved some of the solid sample in deionized water in a test tube. To the test tube, the student added dilute hydrochloric acid followed by aqueous barium chloride. A precipitate was observed. Give the color of the precipitate and the ionic equation for its formation. Include state samples. Okay, include state samples. So they have added barium chloride. I had potassium sulfate. So when barium chloride is going to react with potassium sulfate, that is K2SO4, as a result barium sulfate and KCl would be produced. Okay, so you can see barium sulfate is a solid. You can see barium sulfate is a solid. So we can see the white precipitate, As you know that barium sulfate is insoluble. So I can see the white precipitate, or then we have to write down the ionic equation. Okay, so I would be writing white PPT, white precipitate, and then we have to write down an ionic equation. This is barium chloride, which is aqueous, solid, aqueous. Okay, so ionic equation would be just like that. Okay, I have cancelled spectator ions, so I got this one. I got this one. Okay, this is your ionic equation. Then in B, another student was given a solution containing one type of cation and two types of anion. Okay, the student warmed some of the solution in a test tube before adding aqueous sodium hydroxide and holding damp red litmus paper at the mouth of the tube. Okay, so from the results, the student identified the cation as the ammonium ion. Explain the student's inference. So, we have to write down that when we have taken a red litmus paper at the mouth of the test tube, so, we have ammonium cation. From ammonium, ammonia would be released. From ammonium, ammonia would be released, and ammonia is a basic gas. And ammonia is a basic gas. Okay, ammonia is a basic gas. So that's why, in the presence of basic gas, the color of the damp red litmus paper would turn into blue, like red to blue, like red to blue. Okay, why? So then you are supposed to further explain that this is ammonia. This is ammonia. Okay, because whenever you have ammonium ion and you are going to warm it, so for sure ammonia gas would be released, and we can check the presence of ammonia gas by just having the red litmus paper at the mouth of the test tube. So if the color of that red litmus turns into blue, so it means that ammonia gas is confirmed. This is of 2 marks. This is of 2 marks. Okay. So uh, after warming solution containing ammonium, NH3 gas is released, which is basic in nature. It would turn. It would turn red litmus. It would turn red litmus paper into blue. Okay. To another test tube of the solution, the student added silver nitrate solution. A pale yellow precipitate was observed. If you remember, we have three types of halides: chlorides, bromides, and iodides. After adding silver nitrate, if you can see the white precipitate, mean chloride is confirmed. After adding silver nitrate, if you can see the yellow, you can see the cream precipitate, so the bromide is confirmed. Okay. And after adding silver nitrate, if you can see the yellow precipitate, which means that iodide is confirmed. So in this question, yellow precipitate was observed. The student then added an excess of dilute nitric acid. Effervescence was observed. Some of the precipitate dissolved. The student added an excess of concentrated ammonia solution to the remaining precipitate. The precipitate dissolved to form a colorless solution. Complete the table about the student's result. Okay, so first of all, which gas is evolved? Which gas is evolved? Okay, so what they were saying, another student was given a solution containing one cation, that is this, and two types of anion. Two types of anions. Okay, so and then they are saying the student added an excess of dilute nitric acid. After the addition of acid, we can see effervescence, we can see bubbles. Okay, what they are saying, like effervescence was observed. This is the sign of carbon dioxide. If you remember, we have calcium carbonate which is reacting with HCl or any acid. Carbon dioxide would be released because carbonates are bases. Whenever we add, whenever we add any acid to the carbonate, whenever we add any acid to the carbonate, and if the if we can see effervescence, which means that carbon dioxide is released. Okay, so what I'm supposed to write, CO2. What I'm supposed to write, CO2, that's it. And then they are saying formula of the precipitate that dissolved in dilute nitric acid. Formula of the precipitate that dissolved in dilute nitric acid. So of course, that is supposed to be silver carbonate. That is supposed to be silver carbonate. And formula of the precipitate that dissolved in concentrated ammonia solution. So we have seen in that, to another test tube of the solution, the student added silver nitrate solution, a pale yellow precipitate. A pale yellow. So pale yellow means that it's Br, it's bromide. It's not complete yellow, it's pale yellow precipitate. So it would be silver bromide. It would be what? Silver bromide. Okay. So to do these type of questions, you need to memorize the test for halides. Okay, the test for halides, especially chloride, bromide, and iodide. Okay, so we have two tests. First of all, we add silver nitrate, and then we look at the precipitate, and then after all, we add ammonia. After all, we add ammonia, and then we have to look at the solubility of the precipitate. Okay, each halide have their own solubility in dilute, like few drops of ammonia or excess ammonia. So you have to look over this. So you will be getting your answer. It's very easy. If you have memorized this one, so it would be very easy for you. Okay, and then uh, they are saying, yeah. Question two: A student used the reaction of magnesium with hydrochloric acid to determine the volume of 1 mole of hydrogen gas at room temperature and pressure. So weigh zero point zero 0.03 gram of magnesium ribbon and this. Explain why the volume of hydrochloric acid added to the burette in step 2 does not need to be exact. You must include a calculation. You must include a calculation. Okay. And this is of 3 marks. And this is of 3 marks. Remember. Okay. This is of 3 marks. So they were saying in the question, we have to weigh 0.03 gram of magnesium ribbon and approximately 225 cm cube of 2 mole per dm cube of hydrochloric acid into burette and carefully add 25 cm cube of water on top. Push the magnesium ribbon into the open end of the burette so that it stays in the position. Okay, just like that. And quickly invert the burette, clamp the burette vertically and take the burette reading. Wait for the magnesium to start reacting. Take the final burette reading after all the magnesium has reacted. Um, you know, hydrochloric acid is in excess. Hydrochloric acid is in excess, and magnesium ribbon is in a limited quantity. It's only 0.03 grams. 0.03 grams. Okay, they are saying Why the volume of hydrochloric acid needed to the burette in step 2 does not need to be exact. You must in, of course, this should be in excess. An excess amount is not supposed to be more accurate. Okay, why we have added excess hydrochloric acid to make sure all the magnesium ribbon has been reacted, of course. So they are saying you must include calculation. So first of all, you have to find out the moles of magnesium. Mole of magnesium is equal to the mass, that is 0.030 divided by the atomic mass of magnesium, that is 24.3. So I would be getting the moles that would be 1.2346 multiplied by 10 raised to the power minus 3 mole. This is the mole of magnesium. Okay. Then I'm going to find out the moles of HCl. Concentration multiplied by volume. Or I can say that like according to this equation, 1 mole of magnesium requires 2 mole of HCl. But how much moles I have? So I'm going to use the values of HCl. Volume and concentrations both are given. The volume is 25. You have to convert this into dm cube by dividing 1000 multiplied by 2. Concentration was 2. Yeah. So you would be getting the answer uh, that would be equal to how much moles you have? How much moles you have? Of course, that's gonna be 0.025, right? 0.025 mole of HCl. Let me confirm this. Okay. Yep. 25 divided by uh, 25 divided by 1000 and multiplied by 2. It's 0.05. It's 0.05 mole. 0.05 mole we have in the question. In the question. Okay. And this is the mole of magnesium. According to the equation, the mole ratio between magnesium and HCl is 1 is to 2. If I have this much moles of magnesium, if I have this much moles of magnesium, so how much moles of HCl we would have? So you have to cross multiply this. So you would be getting 2.4692 multiplied by 10 to the power minus 3 mole of HCl. So to react with this magnesium, this much moles of HCl is required. This much moles of HCl is required. Okay. But how much moles I have? 0.05 mole. So 0.05 means that it's greater than this one. It's greater than this one. So I can say that magnesium is in HCl is in excess. Okay. Since we have more number of moles as compared to the required moles, so HCl is in excess. HCl is in excess. Hence, HCl is in excess. Okay. So that's why if HCl is in excess, so no need to take exact amount of HCl. That's the reason they have written 25 cm cube, not 25.0 cm cube. That's why. Since the HCl is in excess, so we are not supposed to take exact amount of HCl. Okay. State why the magnesium does not start reacting as soon as the burette is inverted in step 4. The reason is that when you have inverted that burette into the HCl or water, so suddenly the reaction is not going to start. You know why? Because at the start, magnesium is not in contact with the hydrochloric acid. That's the main point. It's of only 1 mark. And of course, when the magnesium is not in contact with hydrochloric acid, so how can I say that the reaction is going to start? It's common sense. Whenever magnesium would be in contact with hydrochloric acid, so their particles can collide with each other, so that I can say the reaction is going to start. So when you are going to invert your burette, so after spending some time, some few seconds, then the reaction would start. But the question says that does not start reacting as soon as the burette is inverted in step 4. So you know what you are supposed to write? Magnesium, magnesium metal, magnesium metal, uh, you can say reacts slowly with water, or you can say that uh, the surface of magnesium metal is not in contact with hydrogen chloride. Okay, it's of only 1 mark. The diagram shows the burette readings from step 4 and 5. Record the burette readings and hence the volume of the hydrogen gas produced in the experiment. Okay, so from step 4 and then from step 5. So you can see that it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 46 point 1, then 2, then 2.5. So 46.25. Okay. And in this, it's 10, 1, 2, 3, 4, 5, 6, 7. So it would be 10.7. Exact. Up to 2 decimal places, 10.70. And then how much would be the volume? I'm going to subtract it. I would be getting 46.25 minus 10.70. That is equal to 35.55. That's the answer. And calculate the volume of 1 mole of hydrogen gas at room temperature in centimeter cube using your answer to see the reaction equation and the mass of magnesium used in the procedure. Okay, this is of 2 marks. If you remember, when we generally do the mole question, so we have to take the mole ratio to that substance which is the limiting reactant. If you remember, I always give this example. If we have 4 t-shirts and then we have 3 trousers. So how much total suits I would be having? You will say 3. So basically, we get an idea after looking at the limiting reactant. You cannot say that we would be having 4 suits. So from where I can have 1 trouser? I need more 1 trouser to make 4. So this is the limiting reactant. So I can tell the total amount by looking at the limiting reactant. You know what? Why I'm saying this? Because in this question, we have the 2 reactants, magnesium and also hydrogen chloride. Since we know that magnesium is a limiting reactant, so I'm supposed to take mole ratio between magnesium and hydrogen gas. Magnesium and hydrogen gas, of course. Since we know that mass of magnesium is 0.03, so I can find out the moles first. 0.030 divided by 24.3, I would be getting 1.2346 multiplied by 10 to the power minus 3 mole. This is the mole of magnesium. Since according to the equation, the mole ratio is 1 is to 1 between magnesium and hydrogen gas. Between magnesium and hydrogen gas. Okay. So, and then what am I supposed to do in this one? They were saying that calculate the volume of 1 mole of hydrogen gas at room temperature and pressure. Okay. Uh, uh, and they're saying using your answer to C. This is your C, in which I got the total volume that was 35.55. 35.55. So 35.55 means that I have to find out the volume of hydrogen gas for 1 mole of hydrogen gas. For 1 mole of hydrogen gas. Okay. So 1 mole means that this much moles, this much moles of hydrogen releases, releases, okay, hydrogen releases this much volume. So how much volume it would be releasing if I have 1 mole? Because in the question they are saying we have to find out the volume of hydrogen gas which is released by 1 mole in centimeter cube, not in decimeter cube, right? So this is your centimeter cube. So X is equal to 35.55 divided by 1.2346 exponent minus 3. Okay, that would be equal to uh 2.8796 multiplied by 10 to the power 4 centimeter cube. Okay, got it? Then you are supposed to try E part. You are supposed to try E part. Okay, it's of only 2 marks. In this question, they are saying the magnesium ribbon used in step one contained a magnesium oxide impurity of up to 2% by mass. Up to 2% by mass. So explain whether this magnesium oxide impurity could account for any difference in your answer to D from the data book value of 24,000 centimeter cube. No calculation is required. Okay. So, as they are saying that impurity of up to 2% by mass, magnesium doesn't react readily with water because at the surface of magnesium, the layer of oxide is formed, which prevents the reaction of magnesium with water. They're saying explain whether this magnesium oxide impurity could account for any difference in your answer to D. Like in D, I got the volume that is 2.8796, 10 to the power 4 centimeter cube. So they are saying we would be having any difference? Yes or no? No calculation is required, and this is of only 2 marks. So, uh, of course, moles of hydrogen would be very high, of course, because um, they are saying whether this magnesium oxide impurity could account for any difference. If you don't have any impurity, so when you are going to calculate the moles of magnesium, so the mass would be lower. The mass would be lower. When the mass would be lower, so of course the moles of magnesium would be lower. Yes or no? I'm talking about this one. I'm talking about this one. The mass of magnesium was 0.030. The mass of magnesium was 0.030. If there would not be any impurity, so the mass would be less than this, isn't it? So we would be getting the less number of moles. Okay, we would be getting the less number of moles. So we have to write less number of moles of magnesium would be produced, like the moles of magnesium would be smaller in this case when there would be no impurity. And after calculating the moles of magnesium, okay, so of course the moles of hydrogen would be very high. The moles of hydrogen would be very high. Okay, so this is quite clear. This is quite clear, right? Okay. So in this question, the magnesium ribbon used in step one contained a magnesium oxide impurity of up to 2% by mass. Explain whether this magnesium oxide impurity could account for any difference in your answer to D from the data booklet value of 24,000 centimeter cube. Like, you know why they are saying this one? 1 mole of any gas, 1 mole of any gas occupy this much volume, occupy this much volume, right? Okay. So they are saying when there would be uh, no any type of impurity, like they're saying we had 2% impurity. So is there any difference? Is there any difference on the volume of hydrogen gas produced? So, you know, first of all, let's suppose right now we had the mass of magnesium that was 0.030 grams. And this is the mass with the 2% impurity. With the 2% impurity. Okay. So if we have no any impurity, so 100% sure the mass would be less than 0.030 gram with no impurity, isn't it? Isn't it? Right? With no impurity. So we can say that uh, less number of moles of magnesium were produced. Okay, when you would be calculating the moles of magnesium, and let's say the mass is 0.020 grams without any 2% impurity, let's suppose. So when we would be calculating the moles, so I would be getting the smaller answer for moles. I would be getting the smaller answer for moles. So less number of moles of magnesium is produced, of course. But, but, but this is the law. 1 mole of any gas occupy the same volume. 1 mole of any gas occupy the same volume. This is fixed. This is fixed. So there would be no effect on the volume of hydrogen gas produced. Only you would be calculating the less number of moles of magnesium. That's it. That's it. Okay. There would be no difference in the volume of 1 mole of hydrogen gas. Remember, but there would be no effect, but there would be no effect on the volume of hydrogen gas produced. Hydrogen gas produced. Okay. Hydrogen gas produced by 1 mole of a gas. That is fixed. And then two readings were taken to measure the mass of magnesium used in the experiment. The uncertainty in each reading was 0.0025, 0.0025. Calculate the percentage uncertainty in the mass of magnesium used in the experiment. We are taking the reading twice. We are taking the reading twice, before and after. Before and after. This is of only 1 mark. Okay. So always remember you have to multiply this by 2 because we take twice, reading twice. That is this one, and divided by the total mass of magnesium, that was 0.030. That was 0.030. Okay. Then that would be your answer. That would be your answer. percentage uncertainty, I'm supposed to multiply this by 100. So I would be getting 16.7%. Okay. Uh, then the student wanted to reduce the percentage uncertainty by using double the mass of magnesium. By using double the mass of magnesium. Give the reason why the experiment outlined in the procedure could not be conducted successfully using double the mass of magnesium. Using double the mass of magnesium. So how can we say regarding this one? If you are taking double mass of magnesium, okay, the student wanted to reduce the percentage uncertainty. Okay, you know what does it mean? This is called the percentage uncertainty. Listen very carefully. If you are going to increase the mass of this magnesium, of course the percentage uncertainty is going to decrease because they are inversely proportional to each other. Yes or no? They are inversely proportional to each other. So the same goes with this one. If they are saying that the student wanted to reduce the percentage uncertainty by using double the mass of magnesium, give the reason why the experiment outlined in the procedure could not be conducted successfully using double the mass of magnesium. Okay. You know, in the whole experiment, I have HCl in that burette because this is the whole reaction which is happening between magnesium and hydrochloric acid. And this is the size of your whole burette. When you would be taking double the mass of magnesium, so of course you would need more volume of HCl, isn't it? Because they are going to react with each other. So you would need more volume of HCl. So means that as a result, more volume of hydrogen gas would be produced. And when the more volume of hydrogen gas would produce, so most probably this would take the larger, this would take the larger volume. Of course, it may be greater than the burette volume. So then what you do in that case? How can you measure? Like if you can see, they have given you the picture in this one. You know why? Because this is the limited reading. Like, you know, you can count this, you can calculate this. But what if you are going to take double the mass of magnesium? So your whole burette would be empty because you would need the more volume of HCl, and not only this one, but also the more volume of hydrogen gas would be produced. When the more volume of hydrogen gas would be produced, you know what would happen then? The whole burette would be empty just like that. You know why this is empty? This is a gas. Which gas? Hydrogen gas. If you have more gas, so there would be empty burette. If you have more volume, then you have empty burette. So you know the size of the burette is limited, only 50 centimeter cube. So it's quite impossible to take double the mass of magnesium. If you are thinking that I can reduce the percentage uncertainty by looking at the relation that percentage uncertainty is inversely proportional to the mass of magnesium, yeah, that's true. But you have to see your experimental requirements. How much, like what is the total volume of the burette right now that you are using? You have to look over this as well. Okay. So what am I supposed to write in this one? This is of only 1 mark. I'm supposed to write um, by taking double mass of magnesium, by taking double mass of magnesium, okay, more volume of hydrogen gas, more volume of hydrogen gas will produce, which would be greater, which would be greater than the burette volume. Then in next question, the concentration of a solution of barium hydroxide can be determined using a standard solution of ethane dioic acid. State what is meant by the term standard solution. The solution whose concentration is known is called standard solution. Okay. Solution of known concentration. Solution of known concentration. Describe the preparation of 100 centimeter cube of 0.05 mole per decimeter cube standard solution of ethane dioic acid starting with crystals of ethane dioic acid dihydrate. Your answer should include details of the apparatus used and the mass of H2C2O4.2H2O required. Okay, I have to I have to make this concentration solution and the volume should be 100 centimeter cube and the volume should be 100 centimeter cube and this is of 6 marks and this is of 6 marks. So first of all, you are supposed to calculate the molecular mass of this one. Okay, this is the first step that you need to do. Since the MR of H2C2O4 dot 2H2O is 2 into 1, 12 into 2, 16 into 4, and 2 water means 2 into 18. That's gonna be 126. Okay. This is the molar mass of ethane dioic acid. It's grams per mole. Okay. Then I need to calculate the mass. Then I need to calculate the mass in grams of H2C2O4 dot 2H2O. That is equal to concentration times volume. Concentration is 0.05 and the volume is 100 divided by 1000. So the mass would be equal to, uh, first of all, this is the mole, of course. That would be equal to 0.005 mole and then multiplied by MR. That is 26. That is 126. So it would be equal to 0.63 grams. 0.63 grams. Right one? Okay. Then what you have to do, weigh this much mass of H2C2O4 through the weighing balance. And then you have to add this much mass into the volumetric flask. You must use volumetric flask. You are not supposed to use beaker, which is not accurate. You are not supposed to use conical flask, which is not accurate. Okay. And only the most accurate one apparatus is volumetric flask. We always make a solution in volumetric flask. Remember. Okay. So then you have to take this much grams in a volumetric flask. You have to take 100 centimeter cube volumetric flask. Okay. This is called the volumetric flask. This much grams is added to this and this is 100 cm cube. Okay. And then add distilled water into it. Add distilled water into it. Okay. Or then now the solution is ready. You are supposed to thoroughly mix it. So as a result, you have the solution having this much concentration and this much volume. Automatically, when you would be adding water up to the mark, of course, the mark is at 100 centimeter cube. So when you would be adding distilled water up to the mark, so automatically the concentration would be 0.0500 mole per decimeter cube, and the volume would be 100 centimeter cube. So it's of 6 marks. So you have to write it down in a proper manner. Like you have to write in detail. First of all, you have to weigh this much amount through the weighing balance and then add this gram to the volumetric flask, add few drops of distilled water, then shake it, then mix it, and then furthermore add distilled water up to the mark that is 100 centimeter cube. So your solution is ready. Okay, in this manner, we can make a solution. Then name the piece of apparatus that should be used to add the ethane dioic acid solution to the conical flask. To the conical flask. So 25.0 means we are supposed to use pipette. We are supposed to use pipette. The titration was carried out with a few drops of phenolphthalein indicator in the conical flask. State the color change observed from then to. Remember, acid is present in the conical flask. So when you are adding phenolphthalein to the acid, so it was colorless. And in the presence of base, it would be pink. Colorless to pink. The formation of white precipitate was observed during the titration, suggests the identity of the white precipitate. What the reaction is going on? Oh, barium hydroxide is there of an unknown concentration. So when you have barium hydroxide, so remember this was produced barium ethane dioate. Barium ethane dioate, which is insoluble. That's why you can see the white precipitate. And then the titration was repeated, giving a mean titer of 31.55. Calculate the concentration of the barium hydroxide in grams per decimeter cube. Barium hydroxide and H2C2O4 react in a 1:1 ratio. We know the moles of H2C2O4 that we have calculated in the last step. Okay, that was so although the concentration and also the volume was given. Okay, so I think so the volume was 25 divided by 1000 and the concentration was 0.05. So I got the moles, that is this one. This is the mole of H2C2O4. um, and then um, moles of, this is also the mole of barium hydroxide, since the ratio is 1:1. since the ratio is since the ratio is 1:1. Okay, then I need to find out concentration of barium hydroxide. Concentration is equal to mole upon volume. Mole I got 1.25 exponent minus 3, and the volume is 31.55. I have to convert it into the decimeter cube by dividing 1000. So I would be having this much mole per dm cube, that is concentration 0.0399620 mole per decimeter cube. This is the concentration. But they are asking the concentration in grams per dm cube. So what I have to do, I have to convert the mole into grams. I have to convert the mole into grams. So how can I convert mole into grams? Like mole to mass, like mole to mole to mass. So mole is equal to mass upon mr. So mr time moles, like Mr. Moles. Mr. Mole is equal to mass. So what is the mass of barium hydroxide? What is the mass of barium hydroxide? 0.039620. That is the mole multiplied by the mr of barium hydroxide. That is 171.3. So I would be getting 6.79 grams per decimeter cube. That is your correct option. That is your correct answer. Are you getting my point? Okay, this is easy, right? This is easy. Okay. Now see this one. Question number 4. Read it carefully. This question is about the preparation of 2-methyl propane from 2-methyl propane to all and concentrated hydrochloric acid. Okay, this is nucleophilic substitution reaction. Give one reason relating to safety why the hydrochloric acid is added to the separating funnel 3 centimeter cube at a time and not all at once. Not not all at once in step 2. Why? Why this is so? This is of this is of only 1 mark. This is of only 1 mark. Okay. You know, if you would be adding all at once, so it can splash. It can splash, or you can say mixing is exothermic, of course. So it's gonna release too much heat that can harm for you. Okay, and the reaction is going on in some sort of flask. You can say they are saying in separating funnel. Separating funnel. I think so. They should give the picture of the yeah. So this is your separating funnel, okay, like pear-shaped flask. Like there is a difference between this and exact separating funnel. But according to this, I can say that when you would be adding all the hydrochloric acid at a time, so the pressure can build up. That can also harm for you as well. Okay, so you can write any one of the point. You can write any one of the point. So I'm going to write. I'm going to write. Uh, can build up. Can build up pressure. That's why we are not supposed to add all the HCl at once. Draw a label diagram of the separating funnel at the end of step 3. At the end of step 3. Okay, step 3, what they are saying in step 3? Leave the separating funnel for about 20 minutes, shaking it gently at regular intervals. Allow the layers to separate. Allow the layers to separate. You know what is separating funnel? So look at this. Uh, this is just like that. So the layer is produced in this one. You can consider this. Okay. So the layer is produced. This layer is aqueous layer as the density is higher. And this layer is 2-chloro, 2-methyl propane. Okay. Like its density is lower. So of course it should be higher. That's why they have given you the density. And the density of aqueous is high. So it should be at the bottom. Sodium hydrogen carbonate solution is added to remove acid impurities in step 4. Give the reason why a stronger alkali such as sodium hydroxide solution should not be used for this purpose. Should not be used for this purpose. Okay. So you know why? Mhm. In step 4, what's going on? First of all, you have to see this. In step 4, discard the aqueous layer before washing the organic layer repeatedly with sodium hydrogen carbonate solution, releasing the pressure after each addition. Discard the aqueous layer before washing the organic layer. Discard the aqueous layer. Okay. So, when you would be having sodium hydroxide solution should not be used for this purpose. Only we can add sodium hydrogen carbonate solution is added to remove acid impurity, which is a weak acid, which is a which is a weak acid. Okay. So it can only remove an acidic impurity. But if you would be adding sodium hydroxide, that is more reactive, that is more reactive, so it can react with your organic layer. What is organic layer? 2-chloro-2-methyl propane. Sodium hydroxide can give its OH minus. And what the OH minus does? OH minus can displace this chlorine. As a result, alcohol would be produced. As a result, alcohol would be produced. To avoid this thing, you are not supposed to take strong alkali, that is sodium hydroxide. That's why we are adding the weaker acid, that is sodium hydrogen carbonate, okay, to remove an acidic impurity. Are you getting my point? Okay. So what am I supposed to write in this? uh Sodium hydroxide would react with organic layer, with organic layer, okay, which can act as a nucleophile. State the role of the sodium sulfate in step 5. Role of the sodium sulfate in step 5. Transfer the organic layer into a small dry conical flask and add 3 spatula measures of anhydrous sodium sulfate, swirling the flask after each addition. So of course, it's a drying agent. It's a it's a drying agent, right? Or identify 2 changes that must be made to the apparatus shown before distilling in step 6, giving a reason for each change. Water from the tap. No, it's not water from the tap. It should be water out, just like that. It should be water in. If you remember, that's the trend of connecting the condenser. It's a condenser basically. And change one. What I'm supposed to change? Change one. First of all, you are supposed to reverse the water connection. Okay. First of all, you are supposed to reverse the water connection. So the change one is reverse, reverse water flow in condenser. Okay. And what is the reason for the change? What is the reason? Condenser should fill with water. And what is change to? What is change to? What is this? Why is this open? And if this is open, do you think all the vapors are going into this condenser? No. Hardly 30 to 40% vapors are going into the condenser. Where are the remaining 60%? They are escaping through this. So you are supposed to seal seal the head of this pear-shaped flask. Okay, seal the pear-shaped flask. Seal the pear-shaped flask. Okay, and what's the reason for that? What's the reason for that? To prevent escape of gas. Okay, calculate the mass of 2-chloro-2-methyl propane produced in this procedure if the percentage yield is 70%. So the density is this and the MR of this and the MR of this. Okay, this is of 4 marks. First of all, the percentage yield is 70%. Okay, and okay. This is the density. 0.78 grams per centimeter cube. Okay, per centimeter cube. This is the percentage yield of 2-chloro-2-methyl propane produced. Yeah, okay. And is there anything in the okay, okay. Oh my God. Okay, okay, okay. Yep. Pour 9 centimeter cube of 2-methyl propane to all. How much? 9 centimeter cube. So multiplied by 9 centimeter cube. Cancel, cancel. 0.78 multiplied by 9. That's going to give you 7.02 grams. You got the mass of 2-methyl propane to all. This is the mass. This is the mass. Are you getting my point? Okay. So, then what am I supposed to do in this one? Mass of 2-methyl 2-methyl propane to all. Okay, mass of 2-methyl propane to all, right? So this is the percentage yield, that is 70%. And this is the MR of 2-methyl propane to all. So I am supposed to first find out the moles of 2-methyl propane to all. Mole of mole of 2-methyl propane to all, that is equal to the mass divided by MR, that is 74. So I would be having this one moles, 0.0948 mole of 2-methyl propane to all. Okay, I got the moles. I got the moles. Okay, and then since the mole ratio, you must know the mole ratio, right? You must know the mole ratio between 2-methyl propane to all and 2-chloro-2-methyl propane. According to this equation, I think so, they have given equation. Yep. According to this equation, the mole ratio between this and this, 1:1. So I can consider that this would be the mole of this would be the mole of you can say uh, 2-chloro-2-methyl propane, the same thing. Okay, so I am going to find out the mass, that is equal to mole, multiplied by MR. What is the MR of 2-chloro 2-methyl propane 92.5. I would be getting the mass. So the answer is 8.775 grams. Okay. So I have to take the 70% of this one multiplied by 70%. So the answer would be 6.1425 grams. So the answer would be 6.1425 grams. They were asking the mass of 2-chloro 2-methyl propane produced in this procedure if the percentage yield is 70%. So you can do just like that. So that's all for this paper. Inshallah, we will do the next paper in the next class. Okay, thank you.